in a Zoom meeting who was unable to remove his cat filter, so he had to do his discussions with the other lawyers as a cat. That was quite funny. You can look for it.
So, David, on which planet are you sitting? I mean, you see the Earth is behind.
Yeah, I'm actually, I didn't find my Vienna background, which is Schönbrunn. I'm not sure why I don't have it around here. So so I just choose
this one is much better
than the Vienna background.
No, this one, going to the cosmos.
Yeah.
So everyone, you are live on YouTube now. And we have our speaker. Hi, Harvey. Can you check? So I'll make you co-host just in case. And can you check that you can share the screen?
Okay.
Yeah, good.
See that?
Could be bigger.
Can you see that?
Yes.
Yes, perfect.
Excellent. I'll minimize it again.
Great. So maybe you can just unshare your screen for a moment, and then I'll start the meeting. Good morning, everyone. I am already used to Zoom meetings, but I'm not that used to Zoom webinars, and the setup is a little different. So I hope that this thing will not bomb out and that there will be no major problems. For once, as usual, I forget to start recording. Thomas Mealing is there to back me up, but so I just started now. So we're live on YouTube and we're recording. A few months ago, I was still hoping that we're going to do this live in Vienna. And if you were in Vienna today, you would be not disappointed. We have a mild -6 degrees today, which compared to a meeting we had in Krakow a few years back with -25 is really a summer temperatures. So I don't think I have to present you Harvey Rial, that everyone knows him. He's a professor at relatively young Cambridge University. I will not present his title because he's going to present it to us. We still have 3 minutes to go. So if somebody wants to fill in the 3 minutes with some comments before unmuting yourselves. No, nobody wants to comment. So let me just say that I'm really happy that this Central European Relativity Seminars survived 11 years now. And each year we're wondering whether we want to do this again or not. But the number of people that are interested makes it clear that there is some interest. So let's hope it's a useful service to the community. And we're always very happy to hear talks from graduate students, recent postdocs who are just bringing new ideas to the field. So given that, still 2 minutes to go. So I can tell you my mild comic joke, which is a guy which is stopped by a policeman and who says, "Mister, you have been drinking," and the driver says, "Well, it is because you're not respecting social distancing." Anyway, I think. Harvey, maybe you can start your screen.
Okay. How do you want to handle questions? Are people just going to interrupt if they have questions, or are you using the chat?
Well, so is it okay with you if people ask questions?
It's fine with me, but if
Yeah.
they do it using the chat, I might not notice. Well, I definitely won't.
Well, yeah. So Thomas will be there just to monitor this.
Okay.
So, those of you who were with us last year in Gaume, and that was these funny times where you could have real life meetings, might remember a talk by Stefan Hollands about similar topics. So we will have a fresh perspective on the recent developments in strong cosmic censorship by Harvey Rial. Harvey, the screen is yours.
Okay, well, thank you very much. It's always a pleasure to visit Vienna, if only virtually. So I'll be giving an overview of some recent developments in strong cosmic censorship. So in this talk, the first half or so of the talk is essentially going to be a review of the current status of strong cosmic censorship, and then I'll move on to describe the more recent work that I've been involved with, which is contained in the papers listed here. The ones in bold are the ones which I would recommend you take a look at if you're interested in learning more, because these have fairly pedagogical introductions. So the outline of my talk is I'll start by describing the situation with strong cosmic censorship for vanishing cosmological constant. And then I'll come on to the newer stuff, which is some violations of strong cosmic censorship with a non-zero cosmological constant. And then at the end, I will discuss some ways of rescuing the strong cosmic censorship conjecture from these violations. So let's start with zero lambda. So if we have a Reisner-Nordström or a Kerr black hole with a non-zero angular momentum, then that solution can be smoothly extended across a horizon inside the black hole. So here's the usual Penrose diagram for a Reisner-Nordström solution. So this is the region outside the black hole interior, white hole, and the other asymptotically flat region. And so this horizon inside the black hole is this blue line here. And so you can extend across that blue horizon into a region to its future, which I've just denoted schematically by this region bounded by the orange dots here. But the important thing for this talk is that there are infinitely many ways of doing this. So there are infinitely many ways of smoothly extending the Reisner-Nordström or the Kerr solution across the Cauchy horizon, across this horizon, which are consistent with the equations of motion. And so that means that if you have initial data prescribed on a surface like this surface sigma here, which goes from one spatial infinity to the other spatial infinity, then if that initial data is exactly Reisner-Nordström, say, then the resulting solution will be exactly Reisner-Nordström all the way up to this inner horizon. But once you go beyond that inner horizon, there are infinitely many things it could be. There are infinitely many ways of extending the solution. And so the initial data, even if you know it perfectly, doesn't predict what happens when you go beyond that inner horizon. So that inner horizon is referred to as a Cauchy horizon. It's a boundary of the region that you can predict in the Cauchy problem from the data prescribed on sigma. So this fact that you can extend in infinitely many ways is rather worrying from the perspective of determinism. It means that we can't predict the future, even if we know the initial conditions on sigma perfectly. Even if it's perfectly Reisner-Nordström, we can't say what the solution is in this region beyond the Cauchy horizon. So often the reason you don't learn about this when you first encounter the Reisner-Nordström or the Kerr solution is you impose extra conditions on the solution to recover uniqueness. So those extra conditions are usually either spherical symmetry or analyticity. So either of those conditions would be enough to recover uniqueness. But we really shouldn't have to do this. We shouldn't have to invoke extra conditions beyond the conditions present in our initial data. So those are not very satisfactory physically. So a final comment on this Penrose diagram is I've drawn the diagram here for a two-ended initial data surface. If we were interested in a black hole formed by gravitational collapse, then you can just cover up part of this diagram with a collapsing star, for example, and then only the part of the Cauchy horizon at early time, so this section here emanating from future time like infinity, is physically relevant. So mostly we're going to focus on the part of the Cauchy horizon down here. So as I said, this is a worrying situation from the point of view of determinism. So this was first discussed by Roger Penrose, who pointed out that maybe there's a way out here, which is perhaps this behavior is unstable. In other words, the existence of a Cauchy horizon only happens for very special, infinitely fine-tuned initial data. And in fact, there's a heuristic reason to expect the Cauchy horizon to be unstable, which many of you will have seen before, which is that perturbations entering the black hole from outside experience an infinite blue shift at this Cauchy horizon. So here's the usual picture of this. So we have, here I've just shown, this is the black hole exterior, this is the black hole interior. We have two observers, Alice and Bob. Alice is immortal, she lives forever, so her world line ends at future time like infinity here. Bob is quite adventurous, and he's jumped into the black hole, and he wants to find out what happens at the Cauchy horizon. And Alice is sending signals to Bob, so every second Alice sends a radio signal to Bob. These are these purple lines here. So Bob is receiving them as he approaches the Cauchy horizon. Getting to the Cauchy horizon just takes finite proper time for Bob. And as you can see, as he approaches the Cauchy horizon, the signals from Alice get closer and closer together, so that the time between them tends to zero as Bob approaches the Cauchy horizon, and he receives infinitely many signals at the instant that he crosses the Cauchy horizon. So this means that the frequency of the signals as measured by Bob is diverging at the Cauchy horizon, and so there's an infinite blue shift there. So the idea is that if instead of considering signals from an observer, we considered small perturbations of the exterior geometry, then those small perturbations will suffer the same kind of infinite blue shift near the Cauchy horizon in the interior. And so they'll have a large local energy, which will cause a large gravitational back reaction, and maybe that will have the effect of destroying the Cauchy horizon and replacing it by a singularity. So that was Penrose's idea. And you can see what's relevant is the late time behavior of perturbations in the interior, because those are the ones which most directly influence the behavior at the Cauchy horizon in the interior. So if this were true, then this may be a way of rescuing determinism. It would mean that Cauchy horizons only exist for exactly Rice-Nordstrom or exactly Kerr initial data. But if you perturb it, then the resulting solution would not have a Cauchy horizon. So here's a more formal version of the conjecture. So we consider complete asymptotically flat initial data for the Einstein-Maxwell equations. Then generically, in other words, for generic initial data, the resulting solution cannot be extended across a Cauchy horizon. And so if this is correct, this would be quite satisfying, because it's a way of restoring predictability or determinism without invoking extra physics, such as quantum effects. You'd be solving the issue entirely within the context that it first arose, namely classical general relativity. So is this conjecture true? So there's over the decades since Penrose proposed this conjecture, evidence has been accumulating in favor of it. So let's start by looking at linear perturbations of Rice and Nordstrom black holes. So these could be massless scalar field perturbations, or they could be linearized gravito-electromagnetic perturbations. So these are coupled together. So for simplicity, let's just focus on the massless scalar in this talk. And let's imagine, so we introduce some initial data for our scalar field, which is compactly supported on our surface sigma. Going back to my diagram, sigma is this initial surface here. So we introduce a compactly supported scalar field on sigma in the Rice-Nordstrom geometry. So how does the resulting solution for the scalar field behave? Well, outside the black hole, it's well known that solutions exhibit power law decay in these asymptotically flat black hole spacetimes. So these are called late time tails, and they arise from the scalar field scattering off the the curvature of the space-time. And this power law decay is slow enough to be effective in triggering this blue shift instability that I just described at the Cauchy horizon, with the result that the gradient of the scalar field diverges at the Cauchy horizon. And this means that the energy density measured by Bob, or by an observer who crosses the Cauchy horizon, is divergent. And so all of this is in agreement with the picture I just described. And we would expect, when we go beyond the linear scalar field and include the back reaction, that this is going to cause a large back reaction on the metric. So in the 1990s, people went beyond just looking at linear perturbations and studied a nonlinear model. So Poisson and Israel introduced a model, again, for spherically symmetric perturbations of Rice to Nordstrom, in which they introduced a kind of a toy model for the matter which is doing the perturbing. This is called null dust. It's what the name suggests. It's null and it's dust-like. So this is matter that moves along null geodesics. And what they showed is that in this model, they could show that back reaction causes a certain invariant in spherical symmetry called the Hawking mass to diverge at the Cauchy horizon. And it does so in a way which is exponential as a function of an advanced time coordinate. And so that exponential dependence caused them to call it mass inflation. But this implies that curvature scalars, such as the Kretschmann invariant, also diverge at the Cauchy horizon. And so in this simple model, the nonlinear model, one can see that back reaction causes the Cauchy horizon to become singular, in agreement with the conjecture. However, there was something quite surprising that came out of this model, is that it turns out that even though the curvature diverges at the Cauchy horizon, the metric can still be continuously extended across a Cauchy horizon, which means in particular we can still define a Cauchy horizon. So there still exists a continuous extension of the metric across a Cauchy horizon, but now the curvature diverges at that Cauchy horizon. But in particular, this means that the singularity that forms inside the black hole is null, at least at early times. So down here, the singularity would just live along this blue line. And that was a bit surprising, because Penrose's original picture was that strong cosmic censorship would cause well, the singularity inside the black hole would be space-like, as for the Schwarzschild black hole. That turns out not to be true. At early times, at least, the singularity that forms when you perturb the black hole is null. Okay, so more recently, mathematicians have been studying this using rigorous methods. And so the model they focused on is the Einstein-Maxwell equations coupled to a massless uncharged scalar field in spherical symmetry. So we introduced the scalar field here to evade Birkhoff's theorem, so that we can still have some dynamics in spherical symmetry. And the idea is that this is a fully nonlinear model. We're considering nonlinear perturbations, small nonlinear perturbations of Rice and Nordstrom by this scalar field phi. As before, we can take compactly supported initial data for this scalar field on this two-ended initial surface. Then what's been proved by de Fermos is that the resulting nonlinear solution can be continuously and globally extended across a Cauchy horizon. More recently, it's been proved by Luke and O that this extension generically is not C2 at the Cauchy horizon, so the curvature diverges there. But what this means is that in this model where we perturb a two-ended a black hole with two asymptotic regions, the picture we get is exactly like this, where we can extend continuously across this Cauchy horizon, and the curvature blows up on that Cauchy horizon. So it's an example of where the resulting space-time has a singularity which is globally null. It's space-like nowhere. So that again was quite surprising. So that's the picture for nonlinear perturbations of Rice to Nordstrom in spherical symmetry. So this is when we look at perturbations on this two-ended initial surface sigma. But if we only interested in one side of sigma, if we only specify data in one asymptotically flat region, then the same kind of things are true, but they just apply to this early time portion of the Cauchy horizon, which is what I've just been describing. So you have this early time null singularity across which you can extend continuously, but not in C2. So this was for Rice-Nordstrom, but very similar results are expected for Kerr. So a continuous extendability result for Kerr has been proved recently by De Fermos and Luke. So this sounds good. A perturbed Rice-Nordstrom black hole can be continuously extended across the Cauchy horizon, but the extension is not in C2, and so the Cauchy horizon is a curvature singularity, which all sounds like it's in agreement with the conjecture. And so we might say that's great, determinism is restored. This curvature singularity obviously is the end of space-time. We shouldn't really go beyond there. However, it's not quite so simple. And this was realized even in the Poisson-Israel model when Ori considered an observer who approaches this perturbed Cauchy horizon where we have this curvature singularity. So because of the singularity, tidal forces diverge at this Cauchy horizon. But from the point of view of the observer, it's not the divergence in tidal forces that's relevant. What's relevant to the observer is the cumulative effect of those tidal forces. And it turns out that this divergence in the tidal forces is an integrable kind of singularity. And so the total tidal distortion experienced by an observer who approaches the Cauchy horizon can actually remain bounded. And so the observer doesn't get infinitely distorted. So the question is, what happens to such an observer? So to answer this question, we need to say something about the dynamics which dictates the motion of this observer. So we need to specify what the observer is made of, give equations of motion for the matter fields that the observer is made of. And the question is, can we still make sense of these equations of motion at the Cauchy horizon? Would it still make sense to extend the observer across the Cauchy horizon? And if so, then we still have this problem with determinism, even though the Cauchy horizon is a curvature singularity. So to discuss this, we need to discuss the notion of weak solutions of equations of motion. So as we've seen, that the space-time is not C2 at the Cauchy horizon. So the question is, what is the minimal regularity we need to make sense of these equations of motion? In particular, one of the equations of motion will be the Einstein equation. So can we make sense of solutions which are less regular than C2? Well, in mathematics, of course, we know we can. There's the notion of a weak solution. And this is something that's quite physical. So, for example, shocks in a compressible perfect fluid are described by weak solutions of the Euler equations. And so if we apply this to the Einstein equation, then it turns out that the appropriate notion of a weak solution is that what requires that the Christoffel symbols should be locally square integrable in some chart for the notion of a weak solution to make sense. So this motivates Christodoulou's formulation of strong cosmic censorship. So he says that generically it should, although it might be possible to extend in C0, the question is whether it's possible to extend across the Cauchy horizon as a weak solution. So his version of the conjecture says that generically it is not possible to extend across the Cauchy horizon with locally square integrable Christoffel symbols. In other words, it's not possible to extend across a Cauchy horizon consistently with the equations of motion, even interpreted in a weak sense. So if this is correct, then you can't extend beyond the Cauchy horizon in a way that the equations of motion are satisfied. And so determinism is restored.
Harvey, question?
Yes.
So, of course, this fact that you can still extend the metric continuously, is this not a little worrisome from your perspective?
No, because I mean, if I can't make sense of the equations of motion, then that doesn't bother me too much. I mean, my theory is breaking down in any sense because the equations of motion don't make sense. I think that's the way I'd look at that. Whereas, so I think this Christodoulou formulation is very physical, because in the sense it's asking, can we satisfy equations of motion? So does the theory still make sense at the Cauchy horizon? Okay, so this version of the conjecture is believed to be true when lambda is equal to 0. So to summarize, we can distinguish different versions of strong cosmic censorship by the level of smoothness that we require at the Cauchy horizon. So in order of decreasing strength, the strongest version of the conjecture would say that generically there is no continuous extension across the Cauchy horizon. The next strongest version would be this Christodoulou version, which I've just explained, which would say generically there's no extension with square integrable Christoffel symbols. And then weaker than that would be the C2 version, which would say generically there is no C2 extension. And so the situation is that for Einstein-Maxwell theory with a massless scalar field, with vanishing cosmological constant, we know that the C0 version, the strongest version, is false. So you can extend continuously. The Christodoulou version is believed to be true, and the C2 version is true. It's been proved in spherical symmetry. Okay, so that's my summary for 0 lambda. Maybe if there are any other questions about that, I'd be happy to answer them.
There are no questions in the chat at the moment.
No, okay. So let's move on to non-zero lambda, which is the recent work. So I'm going to discuss first the case of positive lambda. With positive lambda, there's a new ingredient that comes in, which is now we have a cosmological horizon. So this is the Penrose diagram for Rice to Nordstrom de Sitter. So this is the region outside the black hole. So this is the event horizon of the black hole. And now you see we've got this new horizon in orange, which is a future and a past cosmological horizon. So if you're in this region 1, if you cross through the cosmological horizon, you enter this region here, and this contains the space-like de Sitter infinity. So over here you have another region and another cosmological horizon, and this diagram can be repeated indefinitely to the left and the right. Up here is the black hole region, down here is the white hole region. And a Rice to Nordstrom or a Kerr de Sitter black hole is very similar to the case for lambda equal to 0, in the sense that you still have this Cauchy horizon in blue inside the black hole, beyond which you can extend the solution smoothly as a solution of the equations of motion in infinitely many different ways. So let's just rerun our heuristic argument for why the Cauchy horizon should be unstable in this new setting with the cosmological horizon. So here I've drawn Alice and Bob again. So here I've drawn Alice crossing the Cauchy horizon, sorry, crossing the cosmological horizon, which you would do in finite proper time. But I could also draw Alice hanging around forever outside the black hole and not crossing the cosmological horizon, in which case her world line would go up here. Doesn't really matter which case I consider. The point is that the signals that Alice is sending to Bob at late time, you can see they're now having to climb out of a potential well, which is associated with this other horizon, the cosmological horizon, which is associated with the exponential expansion of space-time caused by the, or space caused by the positive cosmological constant. So this exponential expansion is redshifting everything. And so the signals entering the black hole at late time have already undergone a very large redshift before they reach the Cauchy horizon, where they suffer this competing blue shift that I discussed earlier. So now we've got a blue shift and a red shift, and so it's not clear which effect is going to win. Does the blue shift at the Cauchy horizon beat the red shift coming from the exponential expansion out here, or does the exponential expansion out here dilute everything, dilute all perturbations to such an extent that there's not enough left to trigger the blue shift instability at the Cauchy horizon? So it's not clear a priori who will win. So this was first discussed some time ago, 30 years ago, by Ian Moss and his student Felicity Meller. So they discussed Rice and Nordstrom de Sitter. Again, they looked at linear perturbations of Rice and Nordstrom de Sitter, and they argued that late time decay of linear perturbations outside the black hole is determined by quasi-normal modes of the black hole. So just a reminder, a quasi-normal mode is a solution with time dependence e to the minus I omega t, which is smooth on the future event horizon and the future cosmological horizon, which means that omega turns out to be complex with negative imaginary parts. So these are solutions which decay exponentially in time whilst oscillating. So they describe damped oscillations of the black hole. So in de Sitter space, the slowest decaying quasi-normal mode actually fixes the decay of generic linear perturbations. And so if we look at the rate of decay of that slowest quasi-normal mode, we define the spectral gap alpha to be the minimum value of minus the imaginary part of omega over all quasi-normal modes. And then one expects that generic perturbations will decay exponentially in time as e to the minus alpha t for a de Sitter black hole. And so this is in contrast with what happens for lambda equals 0, the asymptotically flat case, where perturbations exhibit power law decay. Here in de Sitter, it's much faster. At late times, we have exponential decay of linear perturbations. So the question is this decay, this potentially rapid decay, slow enough to trigger the blue shift instability of the Cauchy horizon? So to analyze that, one can introduce cross-scale-like coordinates near the Cauchy horizon, so that the Cauchy horizon is at v equal to 0, with the black hole interior in the region of negative v. Question.
It's not a question. I mean, I think one of the participants has a question, Maddie.
Someone raised their hand but lowered it again. So perhaps if there's a question, raise your hand again so we can.
Yeah.
Sorry, I couldn't unmute myself. I was just going to ask whether alpha depends on the cosmological constant.
Yeah, so alpha depends on the black hole parameters. So it depends on the
and also the mass, or.
Yeah, it's a function of the background space-time, so it depends on the black hole mass, charge, and the cosmological constant. Yeah.
Thanks.
So it's basically the decay rate of the slowest decaying quasi-normal mode.
Nice.
Good. What Meller and Moss showed is that near the Cauchy horizon, when you propagate generic linear perturbations into the black hole interior, you find that near the Cauchy horizon, they behave as minus v to the power beta. So v vanishes at the Cauchy horizon, where beta here is a constant given by the spectral gap alpha divided by kappa minus, where kappa minus is of the surface gravity of the Cauchy horizon, which is positive in my conventions. And so from this formula here, you can see that if beta is less than 1, then the gradient of perturbations will blow up at the Cauchy horizon, which would be in agreement with strong cosmic censorship. And as you can see, that depends on alpha, which is the rate of decay of perturbations outside the black hole. So the perturbations have to decay sufficiently slowly on the scale set by kappa minus. So to determine beta, you have to calculate alpha. To calculate alpha, you have to calculate quasi-normal modes of these black holes, which requires numerics. So Meller and Moss showed that numerically, most Rice and Nordstrom de Sitter black holes do have beta less than 1. And that would mean that the gradient of the scalar field will blow up at the Cauchy horizon, and then back reaction would cause curvature to blow up in agreement with the C2 version of strong cosmic censorship. However, they also claimed that if you look at near extremal Rice and Nordstrom black holes, then in this case you can have beta greater than 1. And this would, if that's correct, that would entail a violation of the C2 version of strong cosmic censorship. However, we have to say that calculating these quasi-normal modes is actually quite tricky. So to determine alpha, you have to really make sure you found the slowest decaying quasi-normal modes. And techniques for calculating quasi-normal modes back in 1990 were not as good as they are now. So it's not, so the numerics here were perhaps not as convincing as they could have been. But nevertheless, they had this claim. And this was then discussed throughout the 1990s until Ian Moss and some other collaborators, Patrick Brady and Rob Myers, wrote a paper in 1998, which concluded that looking at quasi-normal modes is actually not enough for discussing strong cosmic censorship, and that the C2 version of strong cosmic censorship is actually respected by Rice and Nordstrom de Sitter. Okay, so that essentially ended the story in the 1990s. They concluded that in fact strong cosmic censorship was true because you can't just look at quasi-normal modes. Unfortunately, it turns out that there's a problem with this paper, this conclusion, or the argument in this paper. So I won't describe the argument because it turns out not to be correct. So more recently, mathematicians have returned to this problem. And for smooth initial perturbations, what Hintz and Vashi have shown is that the behavior of linear perturbations at the Cauchy horizon is, in fact, determined by quasi-normal modes, as originally claimed by Meller and Moss. So the original Meller-Moss analysis actually was correct, and it's backed up by this rigorous work of Hintz and Vashi. So in fact, the earlier claim still stands, that it's this value of beta which determines whether or not strong cosmic censorship is respected, and it does just reduce to looking at quasi-normal modes. So if the nonlinearities behave as expected, then the Christodoulou version of strong cosmic censorship will be respected if beta is less than 1/2, and the C2 version will be respected if beta is less than 1. So the question now is, what is the value of beta? And to calculate beta, one needs to determine quasi-normal modes of these black holes. So this was discussed by Cardoso and collaborators at the end of 2017, and they did a careful numerical study of massless scalar field quasi-normal modes for Rice and Nordstrom de Sitter. So as I said, you have to calculate the slowest decaying quasi-normal modes to determine beta. So just a reminder, beta is the ratio of the decay rate of the slowest decaying quasi-normal mode to the surface gravity of the Cauchy horizon. And what Cardoso and collaborators found is that near extremal Rice and Nordstrom black holes have beta between 1/2 and 1. And that means that they respect the C2 version of strong cosmic censorship because beta is less than 1, but they violate this Christodoulou version of strong cosmic censorship. In other words, this result indicates that you can extend across the Cauchy horizon consistently with equations of motion. And so we have a problem. So this was for linear perturbations. There's no reason to expect nonlinearities would cause a problem, and indeed people have done numerical simulations in spherical symmetry of the nonlinear problem and confirmed that is indeed the case. So this conclusion survives, including nonlinearities. So that now brings me to what we did.
Harvey, question.
Yes.
So this Luna work, it's a spherical a scalar field or what is the field here?
Yeah, it's just a scalar field in Rice and Nordstrom de Sitter. Spherical symmetry.
Uncharged. Mm-hmm.
Uncharged.
Okay, yeah. Thanks.
Okay, so now come to our work. So what we did was to get rid of the scalar field, and we discussed perhaps the more physical problem of gravitational and electromagnetic perturbations of Rice and Nordstrom de Sitter, which are coupled together. And so we determined quasi-normal modes for these fields. And what we found was quite surprising, is that we found that near extremal Rice and Nordstrom black holes always have beta bigger than 2. So that means that if we're looking at pure Einstein-Maxwell theory, not only is the Christodoulou version of strong cosmic censorship violated, but so is the C2 version. so that this result indicates that the curvature won't blow up at the Cauchy horizon. The fields can be extended in C2 across the Cauchy horizon if we're sufficiently near extremal. And in fact, it's worse than that. So you can show that generic perturbations are CR at the Cauchy horizon, where the value of R can be made arbitrarily large by taking the black hole to be sufficiently near extremal and sufficiently large in units of lambda, the cosmological constant. Okay, so you can make perturbations as smooth as you like by considering a large near extremal black hole. And so this shows that strong cosmic censorship is very badly violated in Einstein-Maxwell theory with positive lambda. So essentially any version of strong cosmic censorship you can think of is going to be violated by these black holes. Well, when I say any version you can think of, I mean for any degree of smoothness, for any value of R. So that's a pretty bad violation of strong cosmic censorship. That was for Rice and Nordstrom de Sitter, which isn't terribly physical. What is physical is positive lambda, which of course is our universe. What's not so physical is near extremal Rice and Nordstrom de Sitter, because highly charged black holes don't exist in nature. But of course, Rice and Nordstrom is often regarded as a toy model for Kerr. And so the question now is, does this violation of strong cosmic censorship for Rice and Nordstrom de Sitter indicate that there's going to be a problem for the very physical case of Kerr de Sitter? So we studied this. In fact, this is the first thing we did in our first paper. We looked at quasi-normal modes of Kerr de Sitter, and you can do this analytically by considering quasi-normal modes with large angular frequency, so modes proportional to e to the im phi, where phi is the usual angular coordinate in the Kerr solution, and m we take to be very large. So in this limit, you can use geometric optics to calculate quasi-normal modes, and the problem reduces to just looking at properties of null geodesics in these spacetimes. So the null geodesics in question are associated with the photon sphere of the black hole. So this consists of null geodesics which remain forever at fixed r. So these are unstable geodesics, of course. When you perturb them, they either fall into the black hole or cross the cosmological horizon. But in geometric optics, the decay rate when you perturb one of these geodesics fixes the imaginary part of the associated quasi-normal mode. So by looking at these geodesics, we can get an upper bound on beta. Because we have an upper bound on the decay rate of perturbations when looking at these geodesics. And the result is that beta is less than a half, with beta tending to a half in the limit that the black hole becomes extremal. And remember, a half was the critical value for Christodoulou's version of strong cosmic censorship. And so this result shows that for Kerr de Sitter, strong cosmic censorship is respected. Christodoulou's version of strong cosmic censorship is respected. So this physical version of strong cosmic censorship is respected for Kerr de Sitter. So what does this mean in summary is that when lambda is positive, this physical Christodoulou version of strong cosmic censorship is respected in pure Einstein gravity, but it's violated in Einstein-Maxwell theory. So it's respected for Kerr de Sitter, but violated by Rice and Nordstrom de Sitter. And I should have said the perturbations we were talking about here are gravitational perturbations, linear gravitational perturbations. They could have been scalar field perturbations, but you can also do the gravitational case. Okay, so that's a little bit surprising. So that was positive lambda. Let me now say something about negative lambda. So here things are rather different. Again, it turns out that perturbations outside the black hole the decay of linear perturbations can be understood by looking at quasi-normal modes, as for the case of positive lambda. And by looking at quasi-normal modes in 4 dimensions, you can see that the perturbations of an anti-de Sitter black hole decay very slowly. This is because of a phenomenon called stable trapping, which means that null geodesics can orbit the black hole at large distance in a stable...
Harvey, question?
Yes.
So is there an equivalent of the Hintz-Fasci theorem for lambda positive? And when you take lambda negative?
You mean the one relating the decay
The
outside?
linear decay, right? Yeah.
I don't think that's been proved rigorously. I'm tempted to say no.
Okay, thanks.
Well, actually, I don't think it's so relevant. As I'm going to explain why it's not so relevant now. So maybe that will make it a bit clearer. So I will explain what the relevant work is. So the point is that if you look at quasi-normal modes of very high frequency, then the decay rate of quasi-normal modes of very high frequency tends to 0 as you take when I say frequency, I mean angular wave number. As you take the angular wave number to infinity, the decay rate of quasi-normal modes tends to 0, which means that perturbations of an anti-de Sitter black hole decay very slowly. In other words, the spectral gap is 0. This means that generic perturbations of an anti-de Sitter black hole actually decay as an inverse logarithm of the time coordinate, which is even more slowly than the power law decay you get in the asymptotically flat case. So since the decay is even slower than in the asymptotically flat case, you might expect this to lead to an even stronger version of the instability of the Cauchy horizon than is present in the asymptotically flat case. And so it's expected, therefore, that the Christodoulou version of strong cosmic censorship is even more likely to be true for negative lambda than it is for positive lambda, just because perturbations of the black hole decay so slowly. So in fact, you might even wonder whether the strongest version of strong cosmic censorship, that the C0 version, maybe that's true for these anti-de Sitter black holes. So this has been investigated for the case of a linear scalar field with conformal coupling by Christoph Kähler. And in fact, he's proved that the C0 version of strong cosmic censorship is actually false for Rice-Nordström ADS, just as it's false for Rice-Nordström with lambda equal to 0. So this effect, it turns out, doesn't strengthen the instability to an extent that you recover the C0 version of strong cosmic censorship. So in other words, you can still extend continuously across the Cauchy horizon of a perturbed Rice-Nordström ADS black hole. However, if you look at Kerr ADS, then things are much more subtle. So here it turns out that the C0 version of strong cosmic censorship is respected. In other words, you get a blow up of the scalar field at the Cauchy horizon. If the black hole parameters belong to a set which is what Kähler calls bare generic, but Lebesgue non-generic. So roughly speaking, this is a bit like the rational numbers within the real numbers. So if the black hole, so it's a set that's dense, but of 0 measure. So if the black hole parameters belong to this set, then the scalar field will diverge at the Cauchy horizon. You cannot extend in C0. But if they do not belong to this set, in other words, if they belong to the set with non-zero measure, then things are just as for Rice-Nordström ADS, and you can extend in C0. So it turns out that whether or not you think the C0 version is respected depends on which notion of genericity you want to use here. So this is rather surprising. It's conjectured that by Kähler this result will be sharp in the linear theory. Okay, so this is a surprising result for negative lambda. But I should emphasize that the Christodoulou version, the physical version of the conjecture, is expected to be satisfied for these black holes. One of the interesting things you can do with negative lambda is that you can construct black holes in lower dimensions. So in three-dimensional space-time with negative lambda, there's the BTZ black hole, which is basically Kerr ADS in 2+1 dimensions. Okay, so this is a black hole solution which is locally but not globally isometric to anti-de Sitter space, and it plays an important role in the ADS CFT correspondence. So in our final paper on strong cosmic censorship, we studied perturbations of this black hole and asked how they behave. We looked at perturbations of various types. So we looked at scalar field perturbations, but there are more exotic things you could look at, like massive vector fields or massive spin-2 fields. They all behave very similarly. The novel thing about the BTZ black hole is this trapping effect, which causes the slow decay in 4 dimensions, is not present And that means that for BTZ, linear perturbations decay exponentially fast, as in Rice and Nordstrom de Sitter. And so the criterion for the Christodoulou version of strong cosmic censorship to be respected is exactly the same. It's beta less than a half, the same criterion as we had for positive lambda. So the nice thing about this solution is that you can do everything analytically. You can solve all the equations using hypergeometric functions. The quasi-normal modes, their frequencies are all known explicitly. And so what we found is that for any type of perturbing field, the situation is very similar to Rice and Nordstrom de Sitter. So we can make beta as large as we like by taking the black hole close enough to extremality. Okay, so again, we have a violation of strong cosmic censorship, where you can make the behavior at the Cauchy horizon as smooth as you like by considering a sufficiently extremal, near a sufficiently close to extremality black hole. So very similar to Rice and Nordstrom de Sitter. In fact, Franz Pretorius and his collaborator Pandya have done numerical simulations of collapse in 2+1 dimensions, and their simulations are in agreement with what we found in the linear study, and they support the idea that nonlinearity isn't going to change any of this. So we have a bad violation of strong cosmic censorship for the BTZ black hole. So to summarize, we've seen the Christodoulou version of strong cosmic censorship is violated by near extremal Rice and Nordstrom de Sitter and also by BTZ. So the question is there any way now of rescuing strong cosmic censorship? And so I'm going to discuss two ways of doing this. One is classical and one is quantum. So let's start with the classical. And let me emphasize something I've not emphasized so far, which is that in all of this story so far, when I've been discussing perturbations, I've been considering initial data for the perturbation, which is smooth. So all of our perturbations arise from smooth initial data. That's what people have always done when studying strong cosmic censorship. In particular, that's what people do for lambda equal to 0. So what de Fermos and Schlappentock-Rothman have suggested is that a way out, or a way of rescuing strong cosmic censorship, is to enlarge the class of admissible initial data by allowing it to be rough, so not smooth. And so if your initial data is not smooth, then the late time behavior is no longer dictated by the quasi-normal modes. And what you can show is that the smoothness of the solution in the sense of Sobolev spaces generically gets worse at the Cauchy horizon. So you can do this quite explicitly by just writing down some solutions of definite frequency and looking at how they behave. So in particular, if you have some notion of what the minimal acceptable level of smoothness is, and you start off with generic initial data with that smoothness, then generically at the Cauchy horizon, your solution will not have that minimal acceptable level of smoothness. So if you, so as a concrete example, if you insist that your initial perturbation, let's say it's a scalar field, has to live in the Sobolev space H1, then generically it will not be an H1 at the Cauchy horizon. Okay, it will be less smooth. So that in that sense, you can rescue strong cosmic censorship by enlarging the class of initial data to include this rough data. And essentially the only important thing you need in this argument is an inequality satisfied by the surface gravity. So it turns out that the Rice and Nordstrom de Sitter black hole satisfies this inequality between the surface gravities of the Cauchy horizon and the event horizon. And this is enough to guarantee this behavior. Turns out this inequality is also satisfied by Kerr de Sitter, and it's also satisfied by the BTZ black hole. So this argument also works as a way of rescuing strong cosmic censorship for BTZ if you're willing to consider rough initial data. It's surprising that this inequality always holds. There must be some reason for it. I don't know what that reason is. Why this inequality seems to hold for all interesting black holes with Cauchy horizons. So it would be interesting if there was some deep reason for it. Okay, so that's one way of rescuing strong cosmic censorship by considering rough initial data. The final thing I'm going to talk about is a different way of rescuing strong cosmic censorship, which is to turn to quantum effects. So the question is, if we look at Rice and Nordstrom de Sitter or BTZ, can quantum effects help save strong cosmic censorship? And the particular quantum effect I'm going to talk about is vacuum polarization, which is the phenomenon that when you look at quantum fields in curved space-time, even if you put them in some symmetrical state that you might want to regard as a ground state, you'll find that the expectation value of the energy momentum tensor is non-zero. Okay, so when we now take account of gravitational back reaction, which we can do through the semi-classical Einstein equation by putting this expectation value on the right-hand side, then vacuum polarization will affect the space-time geometry. So a long time ago, it was shown in a two-dimensional toy model of a black hole with a Cauchy horizon that this expectation value will diverge at a Cauchy horizon. And so maybe this is a way of rescuing strong cosmic censorship. Okay, so this was just for a two-dimensional toy model. So the question is, could this rescue strong cosmic censorship? Is there a similar divergence for BTZ or for Rice and Nordstrom de Sitter? And is the divergence strong enough? So it's not enough that it diverges, it has to diverge in a sufficiently strong way that you can't extend across the Cauchy horizon consistently with the equations of motion. So that's what we want to discuss. So the first investigation, this was actually something we discussed in our paper on BTZ. So for BTZ, you can calculate this explicitly, at least for the most symmetrical quantum state of a quantum scalar field in the BTZ geometry, so the so-called Hartle-Hawking state. And we showed that in fact, if you have a near extremal black hole, this thing does not diverge at the Cauchy horizon. So one can prove that the vacuum polarization, the expectation value of the stress tensor extends continuously to the Cauchy horizon of a black hole with beta bigger than 1. And remember, beta became arbitrarily large for a sufficiently near extremal black hole. So for a near extreme, so if you have a black hole far from extremality, beta will diverge at the Cauchy horizon, but near extremality, beta remains finite on the Cauchy horizon. And so
question?
Yes.
Is there a feeling that this expectation value might blow up in other states, or is it obvious? Is it clear? Is it?
I'm going to discuss that in a minute. So,
okay.
Yeah, our calculation was just for Hartle-Hawking. So at this stage, you're right. You're correct. We could imagine that maybe there's some other state which would give us something different. But in fact, that's not the case. So anyway, for BTZ, this doesn't help. What about Rice and Nordstrom de Sitter? Well, here the calculation is much harder because the space-time is more complicated. But nevertheless, recent work of Hollands, and Zahn has determined the behavior of the expected value of TAB at the Cauchy horizon for a scalar field in a generic quantum state. Okay, and their result is that the stress tensor diverges at the Cauchy horizon proportional to v to the -2, where v is the Kruskal-like coordinate which vanishes on the Cauchy horizon. So their result is that generically you do have this divergence at the Cauchy horizon for Rice and Nordstrom de Sitter. And they showed that this C here is actually state independent. So this constant here depends just on the parameters of the black hole. Okay, so either you get a divergence for all quantum states or for none. And so they showed for Rice and Nordstrom de Sitter, this constant C is generically non-zero. Furthermore, this divergence is quite strong, v to the -2. It's strong enough to rescue the Christodoulou formulation of strong cosmic censorship for Rice and Nordstrom de Sitter. And so this shows that for Rice and Nordstrom de Sitter, quantum fields do actually give us an effect which is strong enough to rescue strong cosmic censorship. So you might ask, how does this fit in with our earlier BTZ result? Well, it turns out that BTZ is special because this constant C just always vanishes for BTZ. It just turns out that it's always 0. So we don't get this divergence. However, there is possibly still a way of using quantum effects to rescue strong cosmic censorship here, which is to say that, well, for BTZ, this expectation value is non-zero, it doesn't diverge if we're near extremality, but it's still non-zero. So there's still going to be some back reaction on the space-time geometry when we plug into the semi-classical Einstein equation. And when we consider now this deformed geometry, in the deformed geometry, this constant c, there's no reason now why it will still vanish. And so it's now plausible that if we now went to second order in H bar in some sense, then second order quantum effects will rescue strong cosmic censorship. So this argument was made by Roberto Emperan and his student. Okay, so we would, by the first order quantum effects would destroy the special symmetry of BTZ, which gave us C equal to 0. And so when we go to second order, the expectation is that C will be non-zero and we'll see this divergence. Okay, so this is just expectation. These calculations would be incredibly difficult to actually do to confirm this, but it seems like a plausible argument. Okay, so coming to the end of my talk, let me summarize. So strong cosmic censorship says basically that physics should be predictable from initial data. As I've explained, it's very likely to be true for four-dimensional black holes with lambda 0 or negative. I've explained how it's true for four-dimensional pure Einstein gravity with positive lambda, in other words, for Kerr de Sitter black holes. But we've seen that it's badly violated in a pure Einstein-Maxwell theory with positive lambda, in other words, Rice-Nordstrom de Sitter, and also in 3 dimensions with negative lambda by the BTZ black hole. So then to rescue strong cosmic censorship, if you want to rescue it, you can do it classically by enlarging the class of permissible initial data to include rough initial data. And as I just explained, quantum field theory effects can also save strong cosmic censorship. So thank you for listening.
Thank you very much, Harvey, thank you for this beautiful talk and for presenting us to your results on this. So we're ready to take questions.
Piotr, may I ask a question? Can you hear me?
Go ahead, Jacek.
So my question is basic. It's related to singularity of curvature on some hypersurface. For instance, Cauchy horizon. So the metric is continuous, as I understand. So we have space-times on both sides of this hypersurface. Mm-hmm. So in general, in such setup, there exists some shell on this hypersurface. So how it is here? So which means that the Ricci is vanishing, or
there's no kind
of Einstein equations on this hypersurface.
So the Einstein equation is still satisfying. It's kind of like I guess it's the Weyl part of the curvature which is diverging there.
Only Weyl, yes?
Yeah, so the Einstein equations are still satisfied, so they're still determining Ricci. But yeah, it's the Weyl type divergence that's happening there. Well, I guess Ricci's diverging as well. No, so maybe I'm saying that slightly wrong. So the scale, if you look at Einstein gravity with the scalar field, so the model that de Fermos studied, so the scalar field is diverging at the Cauchy horizon. Sorry, its gradient is diverging at the Cauchy horizon. So the Ricci is also diverging at the Cauchy horizon, but it's doing it in a way which still satisfies. Sorry, no, it doesn't still. No, I'm saying this completely wrong. Okay, no, so yeah. The point is that the expectation is Ricci is diverging at the Cauchy horizon, and the energy momentum tensor is diverging at the Cauchy horizon. The expectation value, the expectation is that they are doing this in a way which is sufficiently strong that you cannot make sense of the Einstein equations at the Cauchy horizon. Okay, that's what the Christodoulou version is saying.
Even in distributional sense, yes?
Yes, correct.
Okay, thanks. Mm-hmm.
We have a question from Annegret Berger. Annegret?
Yep.
Hi, Agringert.
Yeah, I just have a question that, well, does this behavior for the Einstein-Maxwell maybe also suggest that this is not the right electromagnetic theory, and maybe it would hold for another one, a nonlinear one or something like that?
I'm not sure that nonlinear. Well, okay. So if you make it nonlinear, I suspect what will happen is that the background solution, so the analog of Rice-to-Nordstrom de Sitter, may no longer have a Cauchy horizon. I'm not sure about that, but by considering a different theory, then the black hole solution itself would change, and so it may no longer have a Cauchy horizon. Then of course you don't have a problem even at zeroth order.
There's a question from the chat by Andrzej Rostworowski. Can you just, I'll read it and then I give my interpretation. So the question is, could you remind why polynomial decay of perturbations is not present for lambda larger than 0? You said that there is purely exponential decay. So
yeah,
probably if you can comment on this rather than remind, because it's not an easy answer, right?
Yeah, it's not, I mean, it's not terribly easy to explain simply, but it's kind of related, I think, to you can see it sort of in the analytic properties of mode functions in asymptotically flat spaces. So from the behavior near infinity, you can see that the mode functions, I think, have a branch point at omega equal to 0. And so this branch point is ultimately what gives you this polynomial decay. But if you have positive lambda or negative lambda, then the behavior at infinity is different. Positive lambda, you don't have to go to infinity because you have a cosmological horizon. So you no longer have this branch point, and so you no longer get this polynomial decay. So that would be one way of thinking about it.
Thanks. We have a question from the audience, Ali Serai. Please unmute yourself.
Yes, thank you. So I wanted to ask, is there a physical intuition why the situation is so different in Einstein-Maxwell theory?
No, I don't really have any physical intuition. It's just surprising that it happens for Rice-to-Nordstrom de Sitter, but not for Kerr de Sitter. I mean, you could also consider, of course, Kerr-Newman de Sitter, and there you'd see a kind of phase transition where for slowly rotating Kerr-Newman de Sitter near extremality, it would be more like Rice-to-Nordstrom de Sitter, and for more rapidly rotating near extremal Kerr de Sitter, it would be more like Kerr-Newman de Sitter. It would be more like the Kerr case. But no, I don't have any intuition for why it turned out like this.
And if you replace the Maxwell field with some scalar field, I don't know if this kind of solution is known, but does the same thing will hold, or?
You mean you want to replace the Maxwell field with a scalar field in the black hole solution, or just when you do the perturbation?
Yes, so instead of considering perturbations of the Einstein-Maxwell theory, Einstein some scalar theory.
Well, so what was done first was you can look at the Rice-to-Nordstrom de Sitter solution and you can perturb it with a scalar field. Is that what you mean?
Yes. Somehow.
Yeah, okay, so that's what Cardoso and his collaborators looked at. So in that case, you see a violation of the Christodoulou version of strong cosmic censorship, but not the C2 version of strong cosmic censorship.
Mm-hmm. Thank you.
We have a question from Piotr Bizań.
Yeah, so my question is that this computation of beta is a purely linear thing. And you mentioned several times that you don't expect back reaction effect to change the conclusions. And it's not, well, as the way I see it, it's as long as, for example, these numerical simulations observe mass inflation, then it's fine. Then you rescued cosmic censorship. But if you don't observe mass inflation, I can't see how you can reach conclusions that you violated cosmic censorship, because you your simulation is always in finite time, and how do you know that mass inflation won't happen for longer times of evolution?
Well, 2 points. So firstly, when we violate strong cosmic censorship, that's precisely the situation where the linear perturbations are very smooth and behaving nicely at the Cauchy horizon, which is precisely when we expect nonlinearities to be most likely to be under control. Okay, so it's precisely when we have a violation in the linear theory that we would expect the nonlinearities not to be important. And it's actually the other way around. It's when the linear theory is consistent with strong cosmic censorship. In other words, when linear perturbations are blowing up, that's a situation where we might wonder whether nonlinearities are doing something different from we might expect. So,
but if you have a real gravitational collapse, then the parameters of your background black hole change in time, right?
Course,
so
yes.
beta changes as well.
Yeah. So when you're doing a linear, if you want to study this using a numerical simulation, what you have to be careful to do is to choose your initial conditions so that the final values of the black hole parameters, in other words, the final Bondi mass and the final value of the charge, lie within the regime where the linear theory indicates that there would be a violation of strong cosmic censorship. So that's what you have to do. So this is what's been done. So by Cardoso and collaborators for the case of Rice-Nordstrom de Sitter in spherical symmetry with the scalar field, but also in 2+1 dimensions in the BTZ case, Franz Pretorius, as I said, has done simulations of collapse, and they've arranged that the final black hole is in this regime where we see a violation of strong cosmic censorship in the linear theory, and they're saying that this is in agreement with their nonlinear results. So nonlinearities are not changing our conclusion.
Thank you. Thank you.
Thank you very much. Next question from Lorenzo Gavassino. Please unmute yourself. Lorenzo? No, okay.
Yes. Good morning. Can you hear me? Sorry,
yes, we can hear you now.
I was having troubles. Good morning. I would like just to ask a question regarding using the scalar field. So the idea is I have some kind of other field and I will create perturbations with that. But we know that the standard model is full of possible fields. We have spinor fields. We have a lot of possibilities. We have also the gluon field that is... So isn't it conceivable that in all these population of fields, there will be some fields that anyway, when you make perturbations with them, you will destroy all this situation and you will manage to prove the cosmic censorship?
Well, first point is that the original motivation for including the scalar field, which I think goes back to Christodoulou, is that it gives a way of evading Birkhoff's theorem. So the idea is that somehow the scalar field is a proxy for the gravitational field, but we'd like to study everything in spherical symmetry, and we can't do that because of Birkhoff's theorem. So we introduced this scalar field, but the hope is that it's telling us something about what would happen when we consider gravitational perturbations in the absence of spherical symmetry. Second thing is that if we look at the standard model, then the standard model is a quantum field theory. The only fields in the standard model that really make sense classically, well, the only field is actually the Maxwell field. Everything else needs a quantum mechanical description because the associated particles are either fermionic, so you can't build macroscopic superpositions of them, or they're unstable. They don't live for very long. So it's only really if you insist on the fields belonging to the standard model, then the only one that you can really discuss classically is the Maxwell field.
Well, but for example, we know that the photon, the Maxwell theory is just the low energy of the electroweak. So, for example, when one takes Reisner-Nordstrom, we already expect that it's not a complete description. Or am I missing something?
No, I'm just saying that to describe the rest of the electroweak sector, the W and the Z bosons, you can't really do that classically because those particles are unstable. You have to, so if you're going to go beyond just looking at Maxwell theory, you'd have to do some kind of quantum field theory calculation rather than just some classical calculation.
Another question from Madi Godasgar. Madi?
No, sorry, I didn't have a question.
Okay. Then Yuri Teistra. We can't hear you, Yuri. Yuri, can you unmute yourself? Or good. Well, if there are no more questions, then Harvey, thanks a lot again for this. Okay.
Can I just ask one question?
Lars, very good.
I mean, genericity is always a problem in these kind of considerations. And you mentioned this at one point, sort of bare genericity versus Lebesgue genericity and so on and so forth. And I mean, which of all these results that you have mentioned is the most solid from the point of view of genericity and so on? Or I have the impression that as long as you talk about some kind of symmetric situation, you're always going to have that problem. And so if you could just comment on what is the most robust result from that point of view.
Well, I think that, I mean, this thing about bare versus Lebesgue genericity, I mean, the point is this was a surprise. This was something completely new where the interpretation would depend on what the exact notion of genericity is. So I think all previous results, it didn't really matter too much. So any sensible notion of genericity would give the same answer. So yeah, so I think it was rather surprising that turned out to be the case in the Kerr-ADS discussion.
Yeah. So because I mean so this bare genericity versus Lebesgue genericity also comes up if you look at you know, like Bianchi cosmologies. And there's been a long-standing problem, you know, to what extent you have a silent singularity in Bianchi cosmologies. I mean, this goes back to you know, this chaotic cosmology conjecture and all that. And this has been analyzed quite recently, and the situation is extremely complicated. You can have in some situations, you know, bare generic behavior, or the conjecture can be satisfied bare generically, but at the same time, you know, Lebesgue genericity can hold. So I don't even have a clear picture, but it seems to me that I found that quite interesting that this now has come up in this situation as well.
Yeah, it's surprising because it doesn't happen for lambda equals 0. So for lambda equals 0, the notion.
It does not. Okay.
It was just that. So it's the only example I think is this Kerr anti-de Sitter. So yeah, it is very surprising.
Right, and I mean, I guess one point that was raised in connection with this Yankee situation is that due to the wild nature of the sets where one behavior holds versus the other, you really cannot draw any kind of physical conclusion from that, because these sets are so intertwined, so to speak.
Yeah, so I think I agree. So in this case for Kerr anti-de Sitter, yeah, it's all linear, of course. So what does this mean for the nonlinear story is very unclear.
Well, so thanks again. we have normally a 2 minutes break, which let's make it 5, right? So I'm going to give the chair over to David Feynman, and I propose that we get a 5 minutes break. So let's start at 11:20.
Okay. Maybe the next speaker, Mr. Grigalios Toyanskas, if I pronounce this correctly, could share his screen already, so we're on the safe side before I run for a coffee. Come back in time.
Very correct
Hello.
pronunciation there.
Well, thank you.
So has that worked?
Oh, great. Yeah, that's very nice. Okay, excellent. So we would be ready to start. So we start at 11:20. Yeah?
Mm-hmm. Yeah.
Okay, great. So I'll just run for a coffee. So
yeah,
then I'll be back in 3 minutes. Okay, so it's 11:20. I think we're starting. So welcome to this to the first session after the plenary talk this morning. Our first session is a British session, as I've discovered. So we started with the plenary talk from Cambridge. Now, of course, for fairness, we have to go to Oxford. Then we go back to Cambridge, and then afterwards we have a talk from London. I think that's quite a nice theme. I'm sure the organizers thought this well through. So it's my great pleasure to welcome everyone to the session. The first talk this morning in this session will be given by Grigalius Taujanskas, and the title of the talk is Large Data Decay of Young-Mills, Higgs Fields on Minkowski and de Sitter Backgrounds. Welcome to the talk.
Thank you. It's a great pleasure to be speaking to everyone today. So this will be a rather short talk, but I will aim to present a sort of complete argument nonetheless. So let me very quickly tell you what I'm going to talk about. So I'm going to first have a lightning recap of sort of Yang-Mills Higgs theory and associated classical results. I will then go on to talk about Ardley and Moncrief's famous L-infinity estimates for Yang-Mills Higgs fields, which will lead on naturally to a conformal patching construction and global existence on the Einstein cylinder. And at the end, to reap the benefits, I will quickly talk about the asymptotics that these results imply. Okay, so very, very quickly, the Yang-Mills Higgs Lagrangian on a four-dimensional spacetime is given by the following expression, where the various quantities, so the Yang-Mills field F is given by the expression there in terms of the Yang-Mills potential A. dA phi is the gauge covariant derivative of the Higgs field phi, and lambda is a positive constant. So I should also say that R here is the scalar curvature of G, and I'm using the convention that my spacetime signature is mostly minus. And I'm also using the Penrose conventions for curvature tensor, so there's an extra minus sign there. And if you believe me, I think all the minus signs work out correctly. So the corresponding Euler-Lagrange equations are the following two systems of equations. The one on the left-hand side is the Maxwell equation, the gauge covariant, or rather the Yang-Mills equation. It becomes Maxwell if your gauge group is U1. And the one on the right-hand side is a nonlinear wave equation for the Higgs field phi. So these equations are conformally invariant. Then they don't have to be conformally invariant. If I had chosen different mass for the Higgs field, conformal invariance would break, but because I coupled it conformally under a conformal transformation, if I rescale my fields correctly, as shown here. So one thing to notice here is that the Higgs field scales slightly differently to the Yang-Mills potential and field. These fields then satisfy the rescaled equations, which look exactly the same as the physical equations, where all the Hatters quantities refer to rescaled quantities on the conformally rescaled manifold. So these equations are hyperbolic. As I already mentioned, the one for the Higgs field phi is already a nonlinear wave equation. The one on the left is also a hyperbolic equation, and one way to see that is to rewrite it in terms of the Yang-Mills potential, in which case it becomes a nonlinear wave equation for A. So they're hyperbolic, and a natural first question to ask about hyperbolic equations is, well, are they well posed? A slightly more interesting question is, perhaps a more precise question is, well, how regular must my initial data be for this well-posedness? And on Minkowski space, we have a famous result by Ardley and Moncrief from 1982, which states that if I take initial data for the Yang-Mills potential and the Higgs field phi to be in H2 cross H1, then there exists a global unique solution on Minkowski space in the temporal gauge. So the work I'm referring to here is the second in a series of two papers by Ardley and Moncrief, in the first of which they prove the existence of a local solution by an iteration procedure. And in the second, they extend the local solution by these L-infinity estimates that I will come on to shortly. So H2 cross H1 initial data is good, but in fact, we can do a bit better than that. And in 1995, Kleinen and McAdam proved a celebrated result, which showed that if your initial data is merely finite energy for the Yang-Mills Higgs equations, then there exists a global unique solution on Minkowski space in the Coulomb gauge. So the gauge here is slightly different. That's because Klein and McAdam were only, were first able to see the null structure in the nonlinearities of these equations only in the Coulomb gauge, although this has since been extended to a few other gauges. In 2002, Tao showed that in fact you can do even better than that and reduce the regularity to HS cross HS minus 1, where S is only allowed to be, only required to be greater than 3/4, although here there is no global statement about the solution, only a local solution exists.
Regardless question?
Yes.
So the H1 the threshold is the energy space, right? Which is kind of very natural. How does this 3/4 come about? Can you comment on this?
So this comes, I haven't actually read the paper in detail, but this comes from these XSB estimates that Tao does and space-time Strickhardt estimates.
So there is no obvious intuition for this?
Not that I know of.
And there is no statement that this is sharp or something like that?
No, so I will say a little bit about that in a second.
Thanks.
Okay, so 3/4 is good. You have local well-posedness, and so as Pepper mentions here, sort of H1 is a natural energy, and you might think, well, are we sort of doomed to local well-posedness if we go below S equals 1? Well, in fact, it turns out no. And in 2009, Kielroy and Tao proved that, at least for the Maxwell-Klein-Gordon equations, you have global well-posedness, where S is only required to be greater than √3/2, but it can be less than 1. So there's various interesting things going on here with the minimum regularity of these equations. Okay, so why should one be interested in in lowering the regularity of the well-posedness results of these equations? Well, I claim that this is a physical significance. One is that the finite energy setting S equals 1 is sort of natural from a geometric conformal scattering perspective. But from a quantum field theory point of view, we would probably like to go down to S equals 1/2, which comes from a positive-negative frequency splitting argument. And so this is conjectured to be very difficult. If I'm not wrong, S equals 1/2 is the critical case there. So I don't think there are any results about that yet. And what is more, we would like to do that on curved space as well, if we would like to study scattering on curved spacetimes. So alas, there are not that many results on curved spacetimes about this, although there are some notable exceptions. So these are a theorem by Choquet-Brohan and Christodoulou, which was published at the same time as Leon Moncrief's results that I mentioned earlier. And these show that the Yang-Mills Higgs equations are locally well posed on the Einstein cylinder for data lying in H2 cross H1. And another notable result is a result by Crochet and Chattard, which says that for pure Yang-Mills equations, the initial data, if you have initial data for the potential in H3 cross H2, then you have a global solution in the temporal gauge. So this argument is somehow a reproduction of Early and Moncrief's L-infinity estimates on curved space, and there are various difficulties that are introduced in curved spacetime. As you can see, there is a loss of one derivative occurring in curved spacetimes that I'll say a bit about in a second. Okay, so how do these L-infinity estimates, at least on flat space, work? So if one goes away and differentiates the Yang-Mills-Higgs equations on flat space, one is able to derive wave equations for the gauge, for the physically relevant fields F and d phi. So I should say that Yang-Mills-Higgs is a gauge theory, so there's a redundancy, especially in the Yang-Mills potential, but the fields F and d phi are somehow regarded as physical. So why are these equations useful? You might say, well, we already had wave equations for phi and A. Well, the reason for that is that is exactly this gauge redundancy. And if we work with F and d phi, then we're able to circumvent that, as I'll describe in a second. So at least on Minkowski space, having these wave equations for F and d phi allows us to express the solution as an integral over the backwards light cone from an arbitrary point. So this is what that integral looks like, and the coloring here is sort of related to the different techniques that I needed to estimate this integral. And the thing that I will mention here is that the blue terms are the most difficult, and the blue terms are the ones that require treatment using something, the Cronstrom gauge. And then that's the point where having F and d phi as your fields really becomes important, because you can make the L-infinity norms of those guys gauge invariant. Okay, so Adley and Moncrief then go on to estimate this integral expression for F and similarly for d phi to derive these Gromwall type estimates for the L-infinity norms for F and d phi, where the coefficients here are polynomials in time, depending on the H2 cross H1 norm of the initial data. One thing that I want to point out here is that there is a factor of the energy appearing here, and that will, so that means that in particular that the energy should be finite for this estimate to be useful. So, okay, it is fairly easy to see that from now, the L-infinity norms of F and d phi do not blow up in finite time by applying a simple Gromwall inequality. And then it's a simple energy estimate to deduce that. In fact, the H2 cross H1 norm of the local solution does not blow up in finite time. And that's because you can take out the L-infinity norms in front of your estimate, and you've controlled them, so you control the H2 cross H1 norm. And so you've extended your solution to a global solution. So can we do these on curved space? Well, as already mentioned, the Khrushchev-Chatin method loses one derivative due to this term that I had underlined earlier. And well, perhaps I don't want to get into the business of doing this on generic curved spacetimes. So let me just think about the conformally invariant, the conformally flat case of the Einstein cylinder, and see if I can use the conformal invariance of the Yang-Mills-Higgs equations. And it turns out that what we can do is localize the L-infinity estimates on flat space and then conformally transport them to the Einstein cylinder. So as I mentioned, there is this factor of the energy in the L-infinity estimates by Ardley and Moncrief. And if we were to localize those, we would somehow have to come up with a notion of a local energy. And it turns out that the correct notion of the local energy is simply the local energy in the light cone that you're doing the estimate over. So you take the supremum of the slices, of the space-like slices of your light cone. And equipped with this definition, it's then essentially a trivial matter to retrace Ardley and Moncrief's estimates to deduce essentially the same kind of estimate, but now the L-infinity norms are confined to a local light cone that from a point that I have chosen arbitrarily in Minkowski space. So this is natural to expect, of course, from domain of dependence arguments and the hyperbolicity of the Yang-Mills-Higgs equations. Okay, so because my point is arbitrary, of course, then this shows that for locally H2 cross H1 data for the Yang-Mills-Higgs equations on Minkowski space, my F and d phi fields are locally L-infinity, at least in the domain of existence of my solution. So what am I going to do with this? Well, So this is where this conformal patching construction comes in. So let me take a small ball of radius r around the origin in Minkowski space, think about its domain of dependence, and let me glue this domain of dependence onto the Einstein cylinder by conformally embedding Minkowski space into the Einstein cylinder. So we end up with the following picture here. So this shaded region is Minkowski space for t greater than 0, and the cylinder is the Einstein cylinder R cross S3, and I've suppressed one spatial dimension here. So I've glued this conical patch k hat onto the Einstein cylinder from Minkowski space. And the key point now is that, of course, in this small conical patch around the origin, the conformal factor that under the embedding of Minkowski into the Einstein cylinder is now essentially equivalent to a non-zero constant. And it then follows after some fairly trivial calculations that the L-infinity norms being finite on Minkowski space locally implies the L-infinity norms being finite on the Einstein cylinder in the corresponding conformally transported cone. And we can perform this construction with this small cone positioned anywhere around the cylinder and patch those estimates together. And altogether, what do we end up with? One can see that you can start with H2 cross H1 initial data on the Einstein cylinder, take such a small conical patch on the Einstein cylinder, map it back to Minkowski space, deduce that you have local H2 cross H1 data on Minkowski space, use the localized L-infinity estimates, and map those back to the Einstein cylinder to deduce that you have L-infinity bounds on f and d phi on the cylinder. So if you patch a number of these around the cylinder, as already mentioned, you end up with these L-infinity estimates on a slab of the Einstein cylinder, where the height of that slab is independent of the size of the initial data, and really only depends on the number of these patches that we choose to patch together. Okay, so from there on, then it's a similar and fairly simple argument to do some energy estimates and deduce that, in fact, your local solution on the Einstein cylinder, which was guaranteed by Choquet, Bruja, and Christodoulou, is in fact global and lives on forever for data in H2 cross H1. Okay, so that's nice and good as a result in itself, but remembering the fact that the de Sitter space and Minkowski space are both conformal to the Einstein cylinder, we can quickly reap some benefits of this. And so here's an expression for the conformal embedding of de Sitter space into the Einstein cylinder. Alpha here is my global, is my time coordinate in the global coordinates for de Sitter space. So taking the regularity of the solution on the Einstein cylinder, I can embed, using this overlap embedding H2 into C0.5, the solution that I have into the space of continuous functions on R cross S3 to deduce that my solution is in fact continuous on null infinity on de Sitter space. So de Sitter space is a space-like hypersurface sitting at a finite conformal time on the Einstein cylinder. And because my solution is then continuous, it is uniformly bounded on Scri. And the only thing that then plays a part in estimating the physical solution is this conformal factor, which appears in front of the rescale solution and introduces an exponential, a factor of exponential decay. And I can do a very similar thing for the Yang-Mills potential, except here I have to have a sort of space-time metric with a reverse sign in the space-like part. Okay, so maybe this relates back to the question that was asked in the previous talk: why is there exponential decay in the case of lambda greater than 0? I can do a very similar construction on Minkowski space, except here I have to introduce a null tetrad to ensure that we treat the null directions appropriately. And here it turns out that the scalar field decays like u to the -1, v to the -1, and the Yang-Mills potential decays. There's a few components of the Yang-Mills potential, and they decay along these null directions polynomially, as shown there. Okay, so the final comment is that, of course, because I've used the conformal method here, is that the conformal transport ensures that I cannot have any magnetic charge at infinity for my solution on Minkowski space. However, this is sort of the lowest regularity one can expect to be able to talk about pointwise decay estimates for these solutions. If you had H1, then you no longer are able to talk about pointwise decay estimates because you don't have a Sobolev embedding into a space of continuous functions. Okay, so I think I've almost run out of time, so let me stop there. Thank you.
So thanks a lot for the very nice talk. You finished exactly on time. Nevertheless, I think we can quickly ask if there are some urgent questions for Grigalius. Yeah, Piotr Bison. Piotr, no, sorry. No, sorry, you have to again. Sorry, I wanted to unmute you, but then you pressed again, so now you have to unmute you again. Yes.
Okay. Sorry. I have a remark and a question. A remark is that in physics by Higgs field, you mean a scalar field which is not vanishing at the vacuum, which is not the case. So I would rather call it Yang-Mills scalar field rather than Yang-Mills Higgs. My question is, if you change the sign of the quartic term in the scalar field, you will have a focusing scalar nonlinearity. And in this case, without Yang-Mills, it is known that there are very peculiar global solutions which decay very slowly. And I wonder if inclusion of Yang-Mills would change this or not.
Sorry, do you mean would I be able to do the same thing if I changed the sign of the constant in front of the quartic term?
Yes.
So yeah, so the answer to that is no, because the positivity of various energies then fails. So that's why I have to focus on the lambda greater than 0. As you say, if you reverse the sign, then you have a focusing equation, and you not only can have very slowly decaying solutions, but I believe you can have solutions that blow up in finite time.
Yeah, sure. Yeah, but you also have solutions which are global and decay much more slowly than the ones you have. Okay.
Yeah. Yeah, and so just to come back to your comment about the Higgs field, this is a lot of people prefer to call it the scalar field, or Ali and Mark would call it the Higgs field, but yeah, because it's massless, it's probably most correctly is called the scalar field.
Okay.
If I may just ask a question,
okay.
I don't know how to raise my hand, so I'm just going to do this. When you're doing this conformal transformation in your I-naught, there is a singularity in the conformal factor. Because there are constraints in the equations, one needs to somehow do something about it. So did you look at that? Do you know anything about it?
Well, so part of the point of this construction is that it's all local, and we don't need to worry about I-naught, because we can always rotate our Minkowski space around the Einstein cylinder to ensure that I-naught is somewhere else, and the data at I-naught of this patch is taken care of by another patch. So the thing that is a consequence of that is that in fact, you're dealing with solutions here which on Minkowski space have infinite conserved energy. And on the other side, if you start with solutions on Minkowski space, then to be able to transport them to the cylinder, you're forcing this strong decay at I0.
But surely, if you have a singularity at one point, then you're going to no matter how you rotate your stuff, it'd still be there. So I don't see how you can shift the singularity by moving things around.
So the singularity is there. It's just that it doesn't affect the solution in my very small patch.
Right, away from the domain of the influence of I naught. But if you want to do things globally, maybe I'm confused about the setup.
Yeah, I ran through it quite quickly, but maybe we can
okay.
talk about
Good, thanks. Mm-hmm.
Okay, so thanks a lot for the talk. We switch to the next speaker. Zoe, can you share your screen, please?
Yeah, let me. I think, yeah.
So that's, yeah, very good. Mm-hmm.
That's okay. And can you hear me okay? Because I'm speaking on the...
Yeah, I can
Right.
hear you. I guess everyone else as well. So it's my great pleasure to welcome Zoe Wyatt from Cambridge to the seminar. And Zoe will be speaking about stabilizing relativistic fluids and spacetimes with non-accelerated expansion. So
great.
Go
Thanks,
ahead,
David.
Zoe.
Thanks. And thank you very much to the organizers for the chance to give this talk, because I always love the Central European Relativity Seminar, even sadly if it's not in person. So the talk today is based on joint work with David and with Todd Olenek and Monash, and it's based on a paper that actually came out about a year ago, but I have to apologize, this is my first talk ever on this paper. So if I say something wrong or something, please forgive me. So I'm interested in shock formation on FLRW type spacetimes. So in particular, I'm interested in cosmological solutions to the Einstein equations, where in particular, I here allow for a cosmological constant lambda. And typically one makes or considers a cosmological principle, which tells us that the universe is spatially homogeneous and isotropic. So there's no preferred points and no preferred directions. And a consequence of that is that the metric takes what's called a Robertson-Walker form. So we have a time interval I and a maximally symmetric three-space sigma, where the metric then takes this following form here. And so this factor A here is called the scale factor. It's going to be very important in my talk. And we say it's expanding if its time derivative is strictly bigger than 0. So here sigma can, for example, be R3 or H3 or S3 or a quotient thereof, and it has constant sectional curvature. Okay. So the strong symmetry in this model implies that the stress energy tensor takes the form of a perfect fluid. So here we have density, which is only a function of time, pressure, which is only a function of time, and a unit time-like fall velocity for the fluid particles. And if you consider the one of the components of the divergence of the stress energy tensor, you get something called the continuity equation, which is an equation here. Now, the Einstein equations then determine, give you some other equations that determine scale factor. And these are a system of two ODEs called the Friedmann equations, which I've written here. And so in this talk, I'm interested in considering a linear barotropic equation of state. So barotropic means that the pressure is a function of just the energy density. And here it's linear because I've got some factor K, which on relativistic grounds needs to be less than or equal to 1. And important cases of this equation of state are those of dust when K vanishes. So there's pressureless, where the pressure is 0, and radiation when K is equal to 1/3. So dust here is describing, let's say, ordinary matter, or cosmologists use it to describe ordinary matter, such as baryons, and radiation is used to describe like a gas of relativistic particles. Okay, and so more generally, we need to have an equation of state relating the pressure and the energy density in order to close this system here of the continuity equation and the Friedmann equations. Okay, so it is something that you do need to impose. So it turns out if you integrate up the continuity equation, you get this expression here is actually a constant. Okay, and so you can see here that as the scale factor increases, the energy density rho should be decreasing. So you have a kind of dilution of your fluid, which is will be important later on. And so it turns out one of the Friedmann equations reduces using this equation 8 to the following expression here in equation 9. And so I'm interested in the rate of change of the scale factor. And so you can see just from this equation that there's like lots of different dynamics you can have depending on the sign of the sectional curvature, if the cosmological constant is non-zero or strictly bigger than 0, and obviously also the number k. So just to give you some example solutions, one of the solutions is that of Einstein de Sitter, which is a dust universe, so a matter-dominated universe. And here we get a scale factor of t to the 2/3. Remember, this is the scale factor squared here in the metric. And so this is an example of what we call a decelerating, a universe undergoing decelerating expansion. I hope that makes grammatical sense, okay, because the first derivative is positive, but the second derivative is negative. And then another, obviously very well-known example is that of the de Sitter space-time. So here you can take a positive cosmological constant, and this can be obviously supported on different 3 spaces, but here I've just put it on a R3, and here we get an exponential factor here with a factor of lambda. And so this is an example of accelerated expansion since the second derivative is positive. And another final example, which is the topic, let's say, of today's talk, is the Milne universe, which here is in vacuum, but it has a linear scale factor, which means it's an example of 0 acceleration. So the second derivative is 0. So this is all very interesting to give you, let's say, different models of the expanding universe. So, you know, exponential expansion or the Milne-like expansion here. But this was all under high degrees of symmetry. And so the goal is really to understand the stability of particular space-time fluid solutions by treating the Einstein relativistic Euler equations as an initial value problem. And so one of the simpler problems you can do, because this is obviously quite a broad goal, is you could fix the geometry. So you could fix the metric to be a Lorentzian metric, maybe a space-time may not be, and just consider the relativistic Euler equations. So here I've just written out the Einstein relativistic Euler equations. So we have the 2 equations here describing the fluid, and we need some appropriate equation of state. So as I said, so one problem is, of course, one simplification is you can kind of remove this equation, so just fix the geometry. Another simpler problem you can do is to restrict to irrotational fluids, which essentially means that their vorticity, a notion of vorticity vanishes, and so you can express the fall velocity as the gradient of a scalar field. And when you do this, the relativistic Euler equations reduce to a quasi-linear wave equation for this scalar field phi. Okay, so this is a system of a wave equation that you can study. And so this has been the topic of a lot of research, understanding the stability of solutions to this system of equations. So I just wanted to mention the previous results to really put our result in context. So if you consider a Minkowski background, so where it's fixed, the geometry is fixed, we actually have small data blow up. Okay, this is a remarkable work by Christodoulou, where he showed that shock singularities can form. So the gradient of your scalar field would go to infinity. And this can happen from very, very small perturbations. And these shock singularities will form in finite time. And there was and this is also known outside of relativistic fluids as well. This is known just for the Euler equations. This is a kind of a classical result from the 1800s. So this is perhaps not overly surprising that the same holds true for relativistic fluids. And then there's a paper by Brouwer, Rendell, and Royler from the 90s where they considered a Newtonian cosmological model. So that kind of makes it a bit easier, let's say, than studying Einstein equations. And they considered a perfect fluid either as a dust or with I think, a polytropic equation of state. And they showed that, and the thing I must emphasize is that they considered the cosmological constant to be strictly bigger than 0. And in this case, when lambda is bigger than 0, they showed that small perturbations of some appropriately homogeneous fluid are globally regular. Okay, so you don't get shock formation, which is obviously in big contrast to what happens in Minkowski. Don't forget that Minkowski is an example of an FLRW spacetime, just with the scale factor being 1. However, they also showed that, they also showed that for lambda equal to 0, that, and in the case of a dust fluid, that small perturbations of your homogeneous fluid solution would lead to finite time blow-up. And so in this case, the scale factor is that decelerating example that I mentioned before from the Einstein de Sitter universe. But the key idea to take away from all of this is that space-time expansion can can suppress shock formation in fluids. Yeah, your space-time is expanding, you're pulling apart the fluid lines, let's say, and preventing them from forming discontinuities. So that's kind of the intuition here. And so this has been, as I said, the basis of a lot of research where people have looked at a quiet fluid undergoing accelerated expansion. So the asymptotics of your background are dominated by some cosmological constants. So things are undergoing accelerated expansion, and have shown, there've been lots of results showing global stability with this linear equation of state. So in particular, one of the first works was by Rodnansky and Speck, and you'll see here a whole host of works looking at different ranges of the parameter K. So here's the radiation case, here's the dust case. And the result of Olenek here is the one that is kind of most relevant to our result, because he developed a new method using Fuchsian techniques, which allowed him to treat this parameter range in more generality. And I should just mention, Todd has a recent paper where he was able to consider K above 1/3, which is interesting because there were numerical work suggesting that that wouldn't be true. Okay, so there's all this result in the realm of spacetimes undergoing accelerated expansion. And that was coming from a cosmological constant. And there are obviously other ways that you can induce that kind of behavior. So one such example is what's called a Chaplin gas. So here you have a fluid with negative pressure. And so that's the thing that's kind of pushing apart the fluid and then driving the metric expansion. And so this is also known to be stable in some appropriate irrotational setting. And I should just mention, all these results have, I've done the history perhaps in the wrong way. A lot of these results have been inspired by work of Ringstrom, who was looking at global stability for Einstein scalar field systems. I can't spell the word for, sorry. Where the potential is kind of acting as a cosmological constant. So here, the V naught here was the thing that was essentially giving you, emulating the cosmological constant lambda. And he also was able to treat power law expansion, where again, it needs to be in the case of accelerated expansion. Okay, so you see that really accelerated expansion has been essential to all these papers. And so this leads me to our result, where we considered a fixed metric background, and we call it Milne-like because it doesn't satisfy the Einstein equations, but it's still a Lorentzian spacetime. And so this is, it has the linear scale factor of A is equal to T. And so we consider a linear equation of state in this massive case where K is between 0 and 0, and we're able to show that the relativistic Euler equations are non-linearly stable to sufficiently small irrotational perturbations. Okay, so this is the first example of fluid stabilization by space-time expansion, but where the expansion rate is non-accelerated. Okay, so where it's a power law type, but non-accelerated. So yeah, we think that's quite interesting.
Sorry, question?
Yeah.
So you're not assuming any symmetries here for the perturbations, do you?
No.
No symmetries, but decay, I imagine, or not decay either.
These will be.
Oh, you're in a torus. Okay, sure. Mm-hmm. Okay.
Yeah.
Mm-hmm.
Yeah. Sorry. Yeah. Sorry. I should have. Oh gosh, what did I just do? Okay, there we go. Yes, torus. So yeah, and so I can also put this this result in context with. It's interesting to put it in context with another paper, which is by Speck, who's obviously worked extensively in this area. And so in this paper in 2012, he considered fixed geometry, so fixed Lorentzian metrics of this form and small perturbations of corresponding background homogeneous solutions. And he was interested in deriving conditions on the scale factor to get stability or possibly instability. And so as an example, if you're in the dust case, he needed very strong decay of his scale factor. In the cases in between, he needed some kind of non-negative function here, which which is, quite important. And when he's in the radiation case, he needed this 1/A to be integrable. Okay, so just a comment is our result is very much not covered by this second case. He's not able to, our result falls outside of this class that he considers. And something also quite interesting is that Speck was able to show that in the radiation case, shocks would form if the scale factor, the inverse scale factor, was not integrable in time. And so obviously 1/T is not integrable in time. So our result shows that this shock formation here is sharp. This is what he's done here is very much K is equal to 1/3. And so our case here is obviously just outside of that. So that is work of Speck, and there's also kind of related work by Way, which does a similar argument, but for a different equation of state. And so I just wanted to mention a really quick comment on the proof. I don't actually remember what time I'm started. I'm sorry.
You should have 5 minutes.
Oh, okay, all right. Well, I've got heaps of time then because I've gone quite fast. So I just wanted to mention a comment on the proof. So in the case of exponential expansion, your kind of causal domains decouple typically. And so a key insight of Ringstrom, I believe, is to use a localization argument. And so this has appeared in lots of the other works in this area where they can kind of localize to some data in some small region and just understand stability in that patch that emanates from there. And this is something that we can't do because we have such slow polynomial expansion. So we use a method developed for the relativistic Euler equations by Todd and Nick. And this is where we transform the equations into a Fuchsian symmetric hyperbolic system. So it's a first order system here. And I didn't really want to go too much into the detail, but let me just mention that kind of the key thing that has allowed us to treat our case is that we allow for these kind of diverging terms here. So I should just say all these terms B0 and these CIs and things like that, these are certain matrices. But in particular, there's a diverging factor here on the left-hand side, which Todd had not considered before. And so including this is what allows us to treat this system. But interestingly, we don't get uniform decay of the solution. So we know that it exists globally, but we don't get the kind of decay estimates that he had in his earlier work on exponentially expanding spacetimes. And so, yeah, so let me just finish by saying that this is what we've shown. So we have global regularity and stability for the irrotational relativistic Euler equations with this equation of state for small initial data in the expanding direction of an FLRW spacetime of this form. Okay, where critically we're in that zero accelerated expansion. And so there's lots of future questions that you can ask with this. So one of these is to, we'd really like the metric to be an actual solution to the Einstein equations and consider the Einstein relativistic Euler equations. So this is work in progress at the moment with David. So we're looking at the stability of Milne as a solution to the Einstein relativistic Euler equation. And something else that is quite interesting is understanding, let's say for power law expansion, so for things of this type where Q is 1 or bigger than 1, that kind of thing, is understanding critical cases here. So at what value of Q do you necessarily get formation of fluid shocks, and maybe trying to understand that in a bit more detail. So with that, I'll finish my talk. Thank you very much for your attention.
Well, thanks a lot. That was a nice talk. It's always good to hear.
You're biased, David.
About my results from you. No, really. Well, so are there questions? Yeah, there's some raised hand.
I've enabled the microphone already.
Okay, cool. So please.
Can I just go ahead and ask the question? Yeah.
Yes, we hear you.
Thanks, Zoe, for the talk. So I had 2 questions. One was I guess for Milne, the 3 space would be hyperbolic, right? Is there a reason why that makes this proof more difficult to consider hyperbolic compared to torus?
I think like Todd's method has just been on the torus, and I suppose in some sense trying to understand how to turn it onto a hyperboloid is going to be quite hard. So I think, yeah, in that sense, that was part of the reason, because it was clearly going to take a lot of effort to understand how we could transform his method onto hyperboloid. I should say the thing that we're looking at here with Meln is using the standard CMC spatially harmonic gauge of Anderson and Moncrief. So I think, and there, in some sense, it seems to be working out. So we'll just have to see. But I don't think, I mean, in some sense, the negative curvature you'd hope would actually help you. Like, I think there's a chance that, yeah, it's gonna, oh, sorry, yeah, that is it. No, I do think it could help you for sure. So it's definitely a question of changing that. I suppose what I was trying to say is it's not clear to me what is the best way to do so. Like, is it just easiest just to go through this CMC SH gauge approach and using the elliptic hyperbolic system that you get there, or should we really go back to Todd's Fuchsian method and try and kind of adapt that? It's not clear to me yet what's the best one to do.
And the second, I guess, sort of related question that I had was the so certainly Speck and Rodyansky and Speck do it on the torus as well. Is there an example of study of Einstein-Euler where people consider just flat infinite space?
Oh gosh. If anyone knows, I'd be happy to hear. As I said, I'm not entirely sure of the literature. I don't think so. And also they're in, I think also in some sense they're in the accelerated expansion regime, so they're not so worried about that.
Mm-hmm.
So
it wouldn't make a difference probably.
That's it. It wouldn't make a difference. So I think the answer would be no, but that's just because of what people have considered, what kind of scale factors people have considered so far.
Okay, thank you. So basically you're saying that there shouldn't be a problem considering.
Yeah, and like in these, I must say, in some of these papers by Speck and Rodyansky, I'm sure they make the comment that they just take T3 for simplicity and they don't see there being an obstruction for doing R3. I feel like I've read that somewhere, but I could be mistaken.
I mean, from what I remember, they say that this means that they can consider any compact space, but they don't make, at least Speck doesn't make a comment about infinite case. But
okay.
Sort of,
maybe there is a difference there. Yeah.
Okay, thank you.
Okay, thanks a lot for the question. So we have Annegret, one question. I think then we have to go to the next speaker.
Well, I just could you just quickly say, so what if k is greater than 1/3, you would expect instability, I guess, but I'm not quite sure now about the previous works that you have mentioned in this direction. So you had mentioned Speck's work of 1/3, but what is there more known about this already?
You mean you mean this case here, kind of if we go above 1/3?
Yeah, exactly. What is the result exactly there? And is it expected to be unstable or only instable?
Right, yeah. So I think there's a paper by Rendell where he conjectured, or he had numerical evidence that you get an instability when k was bigger than 1/3. I think you always need it to be less than 1 for the speed of sound to be less than the speed of light. And so I think it's, so Todd is showing that doesn't hold true, at least between 1/3 and 1/2, but certainly the region between 1/2 and 1 is still open. If that answers your question.
Yeah.
Having said that, I should just say, I think there's the paper by LeFloc and Way, where they look at this Chaplin gas. I was reading somewhere there that they, in some case, actually in this equation of state, they do have the speed of sound equaling the speed of light. So in that instance, they are kind of at that critical point of what they call a stiff fluid. But I mean, it's a different equation of state, so it's quite a different
then you have I have a piecewise equation of state that's different.
Yeah.
Okay, so I'm sorry to interrupt, but we have to go to the next speaker. Thanks again, Zoe, for the nice talk. So I would invite Marika Minucci to share your screen, please.
Okay, can you see my screen?
Yes, we can see your screen and we can also hear you.
Okay.
Okay, great. So welcome to the last talk of this morning session. I'm sorry if we're a bit behind schedule, but I think that's fine. So we have now a talk by Marika Minucci from the Queen Mary University of London. And someone is typing, so someone needs to please mute himself or herself. Not sure who that was.
I'm so sorry, that was me.
Oh, never. Okay, great. So again, so we have a talk by Marika Minucci from Queen Mary, and the topic is stability of Einstein spaces with spatial sections of negative scalar curvature. Welcome to the seminar.
So first of all, thank you to the organizer for inviting me to speak today. My talk is a work about existence, which is stability for the solution to the vacuum Einstein field equation with positive cosmological constant. This kind of space-time, which has been widely studied. One paper, for example, is the one of Fajiman and Kroenke about the stable fixed point for the Einstein flow with positive cosmological constant. But the aim of this work is mainly to show that it's possible to get this result by means of conformal method. In particular, what we do is to consider the space-time mg, where G is a metric such that the trimetric gamma ring is a positive definite metric with constant negative scalar curvature. So the first thing that we do is to try to then embed this space-time that we will refer from now on as the physical space-time into a cylinder whose section has negative scalar curvature. We do this by means of conformal geodesics. For people who are not familiar with conformal geodesics on this physical space-time are a pair of X and a one form beta that satisfy the following equation, which are the conformal geodesic equation. Now, to recast our matrix geodesics on this physical space-time as a conformal geodesic, we consider a parametrization of this form. Then we use this tau also as a new coordinate for the metric P, which is, as I said, is the physical metric. And then by means of a conformal transformation, we have the unphysical metric P ring, which is a metric which is well defined for tau that goes from a certain tau star to infinity. So we realized a conformal bending of this de Sitter-like space-time by means of a conformal factor theta, which is proportional to tau, which is also a time coordinate for our metric. So what we do is to then formulate the conformal Einstein field equation. In this case, what we do is not to consider the conformal Einstein field equation, but to consider the extended conformal Einstein field equation. These extended conformal Einstein field equations are equations which are conformal equation, but they are formulated in terms of the Weyl connection, which is a non-metric torsion-free connection. And the reason behind this is that the use of conformal geodesics together with this Weyl connection, and so with this kind of conformal equation, led us to have and somehow a natural conformal factor out of the conformal class. So we formulate the frame version of these equations by defining these following quantities. So this equation turns out to be conditions on these quantities. But we have also other quantities, which are the fields theta and d, which is defined in terms of this Weyl connection. And they are regarded as conformal gauge field, and they are determined by supplementary conditions. The supplementary conditions are given by the definition of other some zero quantities, which are delta, gamma, and bar phi. So the first step in the study of this equation is to study before the conformal constraint equation. We solve this conformal constraint equation on a three-dimensional manifold S, which is a space-like upper surface on the unphysical space-time. And to do this, what we do is to use adapted coordinates, so an adapted frame. And the result that we get, we will consider the following, and we will consider this result as our initial data in what follows. So we move to the study of the evolution equation. We have two evolution systems. The main evolution system consists of evolution equation for the frame component, the connection coefficients, the rescaled by tensor, and the components of the Schouten tensor, and are obtained by the following condition. We have also an equation for the evolution equation for the covector that defines the Weyl connections from the Levi-Civita connection. But we have also another evolution system, which is the subsidiary evolution system. And we get system once we know that the main evolution equation are satisfied, and then we have supplementary conditions, evolution equation for the additional zero quantities, which are delta, gamma, bar phi. So what we've done is to study in order this main evolution system. By the study of the system, what we found out is that all the evolution equation that we get can be recast as a system of equation for quantities b and phi, which are defined in these terms. But this system can be expressed in turn as a symmetric hyperbolic system by means of definition of U. Also, what we do is to use a sort of perturbative approach in which we consider the solution to the equation U has given by the sum of U ring, which is regarded as the exact, the Sitter-like solution expressed in terms of these conformal Gaussian coordinates, plus U check, which is a small perturbation. So since on the initial hypersurface, we have that U ring star is following, so the equation are automatically satisfied, we get by this approach an equation for a system for the perturbation U check. Then what we've done is to study this equation, and then we have a proposition for the existence and stability of the Sitter-like solution to the extended conformal evolution equation. What we've done is then the statement says that then if we U check star is a small perturbation of the de Sitter-like initial data of the conformal field equation prescribed on S, which are the following, we have that there existed Sobolev norm of this initial data is bounded by epsilon. And then if this holds, we have that then there is unique solution U check in this space. And also we have that if U ring star belongs to an E, which is a bounded open subset of the Sobolev space H to the K, then we have that there is a common initial time, existent time to all the initial condition in a small neighborhood of this given point inside the ball. And eventually we have that if we have a sequence of initial data U check such that the Sobolev norm of this initial data converges to 0, then we have that even the Sobolev norm of the solution U check had converge for tau in this set as n goes to infinity. But how do we prove this? The first step is to consider the manifold itself. The dimensional manifold is compact and smooth. Because of compactness, what we do is to then cover this manifold by a finite number of sets, and we associate to every set local coordinates. Then since this manifold is also smooth, we have that the change of coordinates in the overlapping domain is smooth. Second, we have, if we have this U check defined on S, we have that this U check can be restricted to a particular open subset in our I. Then we can extend this restriction to a function from R3 to Rn and define the Sobolev norm of U check star in the following manner. So once we've done this, we move to consider the initial value problem for the Cauchy problem for this quasi-linear symmetric hyperbolic system. And then since the matrix A turned out to be positive definite and the B are at most quadratic in their dependence, what we have is that all the conditions to Cato theorem are satisfied. So Cato theorem then gives us existence, Cauchy stability, uniqueness result for our initial value problem. But then this holds for all these small balls that covers our manifold. To extend this to the old manifold, we consider the fact that since we have in every ball we have a solution, what happens here is that because of Cato, on the overlapping domain, we have two solutions, they must coincide. So by extending this procedure to all the intersection and to all the patches, what we have is that then the initial value problem is satisfied. And we have, again, Cato existence, uniqueness, and Cauchy stability result. In particular, what we have is that then there is a common existence interval for all the solution in this space. We have that then if this epsilon is measured in 0, and then this tau bullet is common, it's chosen for all the initial condition on the open ball, we have this ball inside D. And then we have also that the solution you check with this initial data, you check star exists in this set, we have that all the solution to all the initial condition exist in this set for epsilon sufficiently small. And then as a result, we have that then if epsilon and this tau bullet are chosen as in B, we have that then we have convergence result for the Sobolev norm of this sequence. And so this is the main result for the main evolution system. But then, as I said, we have another system, which is the subsidiary evolution system. And then as we've seen, since the main evolution system equations hold, we have the subsidiary evolution system, our equation for the following quantities. This equation can be in turn expressed as a symmetric hyperbolic system by defining this overall quantity capital X. And the symmetric hyperbolic system is also such that it's homogeneous in the 0 quantities. And even here, with the same procedure that we used for the previous symmetric hyperbolic system in its corresponding initial value problem, we have that then, by the same reasoning, we can prove that Cato theorem holds. And then since the initial condition is such that all the 0 quantities vanish on 0, they vanish in all the set. And then by this, what we have is that if you had star is the solution to the conformal evolution equation such that this conformal equation is satisfied, we have then the proof of a statement about the propagation of the constraint. That tells us that if this equation holds on the prescribed manifold S, we have that then this implies in turn a solution to U hat for U hat to the extended conformalized self-field equation. So then for what we've seen up to now, the solution to the evolution equation together with the conformal constraint equation, a solution to the conformal constraint equation gives us a solution to the extended conformal I self-field equation. But at the very beginning, we thought about the de Sitter-like space-time. So how do we recover, what is the correspondence between a solution to the extended conformal I self-field equation and our initial space-time? This correspondence is given by the following proposition. So if this set is a solution to the extended conformal I self-field equation for some choices of this gauge field, which in turn satisfies some supplementary condition, and then we suppose that these conditions hold on an open subset U, then we have that this metric is in turn a solution to the vacuum I self-field equation with cosmological constant on the subset U. So in conclusion, we've shown that then these two solution of the nonlinear perturbation equation together with solution to the constraint equation gives us a solution to the extended conformal field equation. And then in turn, we have a solution to the Einstein field equation. So we've seen how a method that is based on conformal equation together with a gauge adapted to the frame and the conformal geodesics, we have existence and stability result for the Einstein field equation. So thank you for listening.
Okay, thanks a lot for this nice talk. Are there questions from the audience? I always have to orient, so do I see?
Yeah, so may I ask a question? So your theorem sounds a bit like a theorem that Helmut proved years ago, but he used it. So the difference is that you're using different differentiability conditions and different setting. Is it, do I understand correctly, or?
What we've done is to, as I said, this kind of problem related to the capacitor-like it's a nice space-time with positive cosmological constants are widely studied in many ways and even with conformal method. But what we want to prove is that by keeping the trimetric completely general, by just requiring that is as negative scalar curvature, we can still get existence, Cauchy stability result for our initial space-time.
I see. So this generalizes Helmut's theorem, who took just plain de Sitter, while you can do this for a more general class of metrics. And also, I mean, in his original version, he didn't use the conformal geodesics and stuff like that. He used the previous formulation, but okay.
Yeah, and also it's very nice because then, since we have an adapter frame, then by means of the Weyl connection, since the frame is Weyl propagated along the geodesics, we have the solution, the evolution follows, literally follows the geodesics.
Okay, thank you very much. Thanks.
So are there further questions? Okay, well, if not, then thanks again for this nice talk. And thanks everyone who gave a talk in this session. And so from the schedule, I understand that we resume by 2 o'clock this afternoon. So I would like to have lunch with all of you now, but it's not possible. So just wish everyone a nice break, and then I see you back, and then Jeremy is taking over the chair. So it was a pleasure. See everyone later.
Thank you.